So we're happy to have Ziruo from CISA talking about the entropy of black holes from the superconformal index.
Okay. Yeah, I want to thank the organizers for this opportunity to speak. And today I'll be presenting some work that was done in collaboration with my supervisor, Francesco Bernini, a fellow student, Somon Soltani, Alberto Zaffroni at the University of Milano Bicocca, and his student, Eduardo Colombo. I'll first summarize the results. So in the context of ADS CFT, the entropy of a black hole is the logarithm of the number of dual CFT states. And we'll consider the dualities where on one side there is type 2p string theory on ADS5 times a 5-dimensional Sasaki-Einstein manifold, which is just the base of a Calabi-Yau threefold, a conical Calabi-Yau threefold. And on the other side are particular 4D n=1 superconformal gauge theories. The limit that we will examine is when the rank of the gauge group is large and when the 't coupling is fixed but large, so that gravity is approximated by a classical supergravity. We are then interested in rotating electrically charged black holes in the supergravity, asymptotically ADS5 black holes, which are also supersymmetric and they preserve one complex supercharge. So even though the CFT will be strongly coupled in this limit, we can compute a protected quantity that is the superconformal index at weak coupling, and the answer would stay the same when the coupling is ramped up. And we then rewrote the index in a special form known as the Bethe ansatz formula and extracted one particular term which we expect to reproduce the black hole entropy. In the simple case of the conifold, whose base is called T11, we found that the near horizon geometry as determined by the refractor mechanism exactly matches the field theory prediction. So how do we extract the entropy from field theory? Supersymmetric black holes with a given set of charges are dual to a collection of PPS states in the CFT with the same charges. So here J1 and J2 are two angular momenta corresponding to the two Cartan generators of SO4, and Q are electric charges. To find the black hole entropy in field theory, we will have to count the number of these states. And as mentioned, we will do this by studying the superconformal index, which is shown here, and it is defined as a trace over the Hilbert space in radial quantization, where F is the fermion number, P and Q are angular fugacities, little r is the superconformal R charge, and Y are the fugacities corresponding to global charges. And the index is a function of these fugacities, just like how a grand canonical partition function is like in thermodynamics. And then the degeneracy of states with a given set of charges is obtained via the Fourier transform of the index with respect to the chemical potentials tau, sigma, and delta, which are the logarithm of the fugacities. And the degeneracy of states will then be equal to the exponential of the entropy. So we will find that the index scales as the exponential of n squared, and the charges also scale as n squared. So to obtain the result at leading order in n, it is sufficient to compute the integral using the saddle point approximation. In other words, it's just the extremal value of the following entropy function after extremizing with respect to the chemical potentials. And it's important to note that the chemical potentials must be constrained in a specific way to preserve supersymmetry. And we notice that this is just a Legendre transform of the logarithm of the index. And schematically, the procedure on this slide is just the standard result in statistical physics that the microcanonical free energy, which is also the entropy at zero temperature, is the Legendre transform of the grand canonical free energy. So all that's left to do is to compute the logarithm of the index at leading order in n. And to do this, we'll make use of the Bethe ansatz formula that Bernini and Milan found, which is technically only valid when the angular chemical potentials take a specific form where the angular fugacities, the angular chemical potentials are integer multiples of a complex number of omega in the upper half plane, and where the integers a and b are co-prime. However, it turns out that this restricted set of fugacities is dense in the full set of fugacities, so the formula can be extended by continuity. The result is that the index, which is perturbatively computed as an integral over the maximum torus of the gauge group, can be rewritten as a sum over the solutions to a particular set of so-called Bethe ansatz solutions. Sorry, let me go back. Yes, so inside the sum, we have the original integrand and the Jacobian factor h. And the original integrand is just a product of special functions called elliptic gamma functions. And the unknowns u that we have to solve for in the Bethe ansatz equations live on a torus with modulus omega. And in the sum, we have a sum over these solutions on the torus, and also a sum over integer shifts of each solution by multiples of omega from 1 up to AB. And the integrand is evaluated on the shifted argument. So what we did was to pick out a specific term in this sum and conjecture that it dominates the other terms in the large n limit. And so its logarithm will reproduce the black hole entropy. The term that we picked out corresponds to the solution that is evenly distributed on the B cycle of the torus. These U's, remember, are valued in the maximal torus, and so we have as many of them as the rank of the gauge group. So by evenly distributed, I mean letting these variables take values that are evenly spaced on the B cycle. And one can show that this is a solution to the Bethe ansatz solution equations. In addition, we chose to shift them by I mod AB, where again, I ranges from 1 to the rank of the gauge group. For toric quiver gauge theories, which is a subset of possible holographic quivers, the part that is leading in n inside the term that we have picked looks like the following, where C, A, B, C are top anomaly coefficients of the theory. More generally, for holographic quivers which are not toric, we also have a more general formula written in terms of the central charge A. So this is the field theory prediction, but does it actually reproduce the entropies of black holes in the dual supergravity theory? The answer has already been checked in the simplest case where the Sasaki-Einstein manifold is S5, where there is a consistent truncation called the STU model, and Kutowski and Rial have constructed black holes in such theories. And it has been shown in the paper by Hosseini, Hristov, and Safroni that the entropy of these black holes is exactly reproduced by extremizing the function. The question is that, can the formula also be checked for other examples? So a slight problem is that for the cases where the Sasaki-Einstein manifold is not S5, the dual supergravity theories contain hypermultiplets, and supersymmetric black hole solutions in such theories have not been constructed. So we seem to have nothing to compare to. There's one exception in that one can truncate away the hypermultiplets down to minimal gauge supergravity, where black holes of Kutowski-Rial type are still solutions. And these black holes have one single charge corresponding to the superconformal R charge of the field theory, and one can indeed check that their entropy is reproduced by the Legendre transform of the index. However, we do not actually need to have the full solution to determine the entropy. We just need to have the near horizon metric. So in Hosseini et al.'s paper, they have a procedure to do this, which I will explain. So rotating charged black holes in 5D are a fibration of ADS2 over S3. And at this stage, we are just assuming that such solutions exist, although they have not been constructed. And parametrizing the S3 as the hot vibration of a circle over S2, we can dimensionally reduce on the circle to obtain a black hole in 4D that has the same entropy. Under the reduction, the difference between the 5D angular momenta becomes the 4D angular momentum. This means that to get a spherically symmetric black hole in 4D, we need to restrict ourselves to black holes with equal angular momenta in 5D. We want to get spherically symmetric black holes because then the entropy and also the values of the scalar fields at the horizon are determined via an extremization principle called the attractor mechanism. So if we are able to match exactly the function that the attractor mechanism tells us to extremize with the logarithm of the index that we got from field theory, the Bekenstein-Hawking entropy would have been matched with the counting of field theory microstates. So to check this, we then focused on the next simplest example other than S5 to apply this procedure, which is the conifold. The duality we are considering is then between type 2p string theory on ADS5 times T11 and so-called Klebanov-Witten theory, which has a flavor symmetry that is SU2 times SU2 times a U1 baryonic symmetry. And Kasani and Faedo have obtained a consistent truncation on T11 that is a gauge supergravity with 2 vector multiplets and 2 hypermultiplets. It so happens that on the ADS5 vacuum of this theory, one gauge field is massive while the remaining 2 are massless. And the 2 massless gauge fields are dual to the field theory R charge and the field theory baryonic charge. So in this theory, we can then consider hypothetical black holes with electric charges under the 2 massless gauge fields, and also equal angular momenta so that we can dimensionally reduce and apply the attractor mechanism. Without presenting any detailed formulas, it turns out that the extremization problem of the attractor mechanism exactly matches with the field theory prediction. Lastly, I just want to mention that in matching the field theory prediction with the attractor mechanism, we have made full use of the ADS CFT dictionary by first matching the CFT charges with the 5D supergravity charges and then reducing these charges down to 4D to make the correct identifications. I'll conclude with some future prospects. As we have seen, the lack of explicit black hole solutions in supergravity theories with hypermultiplets has forced us to take a detour and use the attractor mechanism after dimensional reduction. It would have been nice to construct these basic solutions so as to compare their entropy with field theory predictions directly. There has been recent developments regarding an attractor mechanism for rotating black holes in 4D, so it might be possible to perform a more general check in supergravity for the entropy function of 5D black holes with non-equal angular momentum. It might also be interesting to compute corrections to the Bekenstein-Hawking entropy in both supergravity and in field theory and check that they actually match. It's also interesting to examine the entropy of near extremal and near BPS black holes from field theory. Thanks a lot for listening.
Okay, thank you very much. Very good. So are there any questions or observations for Ziruo? So maybe I have one small question. So did you mention that these solutions, they have hypermultiplets, right?
Yes.
The black hole solutions. So, so you have 2 hypermultiplets. Do you truncate many of the hyperscalars, or do you let them all run?
Yeah, in this, when computing the near horizon geometry, we have so we have fixed them using so one of them will be Higgs, and it makes one of the vectors massive, and the other one can be fixed using one of the equations in the attractor mechanism.
Okay, I see. So you're saying that basically, okay.
Yes, and this is I'm just talking about their values at the horizon. So yeah.
Indeed, because you don't have the full solution, you have the near horizon geometry.
Yes.
Indeed. Oh, okay. Because you also were mentioning that you have the minimal solutions with 2 angular momenta, right? Before.
Sorry, I was cut off for a moment. Yes, sorry.
Broke off. Yes, don't worry.
So you were asking about the solutions in minimal gauge supergravity, or?
No, it was a general observation. You have 2 kinds of solutions. One, which in 5-dimensional has 2 angular momenta, and the one near horizon geometry,
yes,
which has 2 coincident angular momenta, right?
Yes.
It seems to me that the first solution, all the scalars are just constant as they are in the vacuum, but yeah, it's just an observation. In the second case, the scalars have a different value at the horizon with respect to what they have at what they will have at asymptotic ADS, right?
Yes, I would expect yes.
Okay.
Yes. Yeah, we have not tried to solve for the flow from the horizon to the asymptotic ADS. So we do not know what it looks like.
Okay, okay. Any other observations or questions? I think we have 2 minutes before we are slightly early.